Chapter 11, more organic synthesis. But this time, we're going to introduce the concepts of multi-step synthesis. And toward the end of the chapter, we're going to get into the concept called retrosynthesis, which is a technique that organic chemists use to develop a synthetic steps. All right. All right, we covered that already. And most of the reactions we've covered so far, although with a few exceptions, were functional group transformations. And while they're very important to organic synthesis, you'll notice that most of the synthetic targets have substantial carbon skeletons. And if we go by the one rule of thumb, which is use cheap, readily available starting materials. And those are usually 3 or 4 carbons. And if you want to make something bigger than that, you've got to synthesize it, which means you need reactions that will extend the carbon skeleton. All right. And our focus on carbon skeleton extension is sigma bonds. You got to have the sigma bond before you can do anything with it. So once you got the sigma, then if you need a double or a triple bond, you can deal with that afterwards. And we're going to look at multi-step synthesis in this chapter, including some earlier carbon-carbon bond forming reactions. And then we're going to take a look at the retrosynthesis analysis technique. Actually, Dr. Carty calls it a strategy. Okay, we'll give him that. And in order to do that, we're going to have to introduce some new chemical reactions. All right, just to try to get you interested in this. Taxol is a cancer chemotherapy drug that was discovered in the Pacific yew tree. There are other natural products that we could talk about, but I'm just going to skip over those. Menthol, eugenol, peppermint oil, and clove oil, and such things. The problem with the Taxol is you have to kill a whole tree just to get a 300 milligram dose for one person. So the race was on to develop a synthetic route to develop to synthesizing Taxol. And eventually, a chemist at Florida State University in 1994 published the first synthetic route for Taxol. The one major problem is it took 46 steps. And we're going to find out, I think it's in chapter 21, that the more steps you have, the less your efficiency. Remember, in general chemistry, we talked about efficiency as what's expected in the denominator, and what's in the numerator is what you actually get. That's the measure of your efficiency. And if you've got 46 steps, I bet his efficiency was just a fraction of 1%. So people kept working on it. And eventually they came up with other synthetic pathways that were fewer steps and, of course, consequently higher efficiency. But you can see it with a molecule that complex, it's going to take quite a few steps. And my guess is it took 12 years for Dr. Holton to come up with this procedure, because he probably went down a whole host of different rabbit holes and found out by example, by failed syntheses, that he had to go back up maybe 2, 3, 4, 5, 10 steps and take another stab at it. All right. These are a couple of reactions. I think we've looked at these before, where we have an alkyne and an alkyl halide come together. And which one is the nucleophile? Well, we're going to make a nucleophile out of the alkyne. What we need is sodium hydride to strip off a hydrogen from the terminal alkyne. So we take that hydrogen, we strip off the hydrogen, and we leave a lone pair behind. So that makes that alkyne electron rich. It's the nucleophile, the attacking species. And then it will attack the alkyl halide because the halogen has an electron removing effect from the alkyl group. So that makes it electron poor. And then the reaction itself is SN2. The other possibility is to the alkyl halide is one of the precursors, and then we attack it with cyanide, sodium cyanide. And notice that when we write these reactions, we're putting the complete compounds in there. Sodium hydride in one, sodium cyanide in the other. This is not a mechanism. This is an elementary reaction. It's a single step reaction that's being described. And then the nitrile attacks the R group, and the halide is the leaving group. And they're both SN2 reactions. And that way we extend the carbon chain. Now, the difference between the two that's obvious to me is the first example where we use an alkyne, you don't have to deal with that nitrogen unless you want it. If you want the nitrogen on there, then the second one is probably your preferred technique. But the first one, if you don't want to deal with that nitrogen after the reaction, then you probably want to go the first route. We're going to introduce a couple more. This would be an example of a two-step reaction. See, we've got the first step is the sodium hydride to make the nucleophile, the alkyne nucleophile. And then the second step, we add the alkyl halide. So actually, I misspoke earlier. It wasn't a single step. It's a double step, because we have to create the alkyne first, the attacking group. And we've created a carbon-carbon bond. Now, below it is the mechanism. Remember, in the mechanisms, we're only interested in the barest minimum for the substrates and the attacking group. So we have that hydrogen ion, anion, without the sodium. It creates the alkanite ion, and that attacks the alkyl group, and iodine leaves. Okay. So the first step is a deprotonation, and the second step is your SN2. Now, do we consider that alkanide a very strong nucleophile, or just a moderately strong nucleophile? As it turns out, that is a very strong nucleophile. And we base that upon the fact that it has a very high pKa. It doesn't want to get rid of that hydrogen. So when it does, it makes, remember, a weak acid produces a strong conjugate base. And in this context, the first reaction, we are deprotonating it. So that's an acid-base reaction. But it produces a very, very strong base as a consequence, or very strong nucleophiles also. Now, there are occasions where the strong nucleophile doesn't necessarily mean a strong base, right? But in this case, they coincide. So this is where we've taken the second reaction and attack that alkyl bromide, we attack the carbon, and the bromine leaves, and we form a new carbon-carbon sigma bond. Okay. Things to look for when you're trying to form a carbon-carbon bond. You actually look at the product that you want for that particular step, and you say, okay, I need to form this carbon-carbon sigma bond, and look for clues to which the reaction could be used to make that bond. And then you say, all right, what precursors can I use to accomplish the formation of that bond? Now, if you're stuck with multi-carbon precursors, then you're probably going to have to back up and construct the precursors to that reaction. So that's always a possibility. Excuse me. All right, I'm not so sure about that. You will quickly be able to draw the precursors. That's our target. We should be able to do that, but I don't know if that's right. So here we introduce the concept of the retrosynthetic pathway. And there are some conventions that we use. For if we pick the first reaction that we studied for forming the sigma bond with an alkyl group, and then we look at the end product and put that first. So we move this top one here and put it down over here. So we flip the reaction. And we say, all right, what bond are we trying to form? So that's where the squiggly line comes in. That's the bond we want to form. And then we put not a double barbed arrow, a fat arrow to represent where we're doing things in reverse. And then in the retrosynthetic scenario, we pick our precursors to give us the formation of that bond. That's the general pattern for the retrosynthetic technique. Let's see. All right. All right, I've already said that. All right. Oh, they call it open arrow. Open arrow. It's called the retrosynthetic arrow. We draw it from the target to the precursors. And I mentioned the squiggly red line. That identifies, and it's good to use that because that identifies which bond you're trying to form in the process. Okay. So if we did this with the second reaction that we know by, we want to form a, excuse me. Let's see. I'm trying to not say cyanide bond because that's not what it is. What's the other term we used for cyanide? Nitrile? I think it's nitrile. We form that bond with the R group, and we show where the bond is going to be formed, and then we say, all right, what materials will give us that? So we have an alkyl halide and we have the sodium cyanide. And those, when we write this out, we're doing it in with the synthetic conventions, right? We put everything in there that's needed. Sodium cyanide, right? This is not a mechanism yet. I mean, we can construct a mechanism from it, but that's only to help us get to the synthetic pathway. All right. Now, sometimes more than one bond could be our target, right? At the top of the page, we have the bond we want to form is the methyl group attached to the alkyne, right? And we could do it that way with just attaching the methyl group. But what if we instead we wanted to use precursors that were a moderate in carbon chain length? Then we might break the bond on the other side of the alkyne. That's the one actually in the retrosynthetic terminology break that bond, but we're actually forming it. That means that we would have a different alkyne and a different alkyl halide. So we can form the same product. We just use different precursors. Okay. Now we're going back to using this technique with functional group transformations. Right. If we want to form an ether, then we could possibly use the Williamson ether synthesis, and that would break the bond between the alkyl carbon and the oxygen attached to the other alkyl group. And the other alkyl group is going to be the attacking group. So we know it's going to be an oxyanion, and then the alkyl group is going to have attached to it a leaving group of some kind. We put an X there. X usually means halide, but it doesn't necessarily have to be. All right. So you examine the target for some feature of a reaction that you know. Right? So some synthetic chemists have just a whole library of reactions in the back of their heads and that they can go to. Others of us, like newbies, we only have a smaller set of reactions that we can deal with. So you go with what you know. And then you take your target and say, all right, what's the transformation I need to get there? Right? You use the conventions that we've discussed. And then you look at each precursor to see if it has the features that you need for the reaction that's expected. And you look for traps. We're going to talk about traps in a minute. Like different, like primary, secondary, tertiary carbons, pi bonds, multiple hydroxyls on different carbons. Those types of things can give you an outcome that you're not expecting. So you look for the precursor features that will satisfy, but won't give you the wrong reaction, right? Those side reactions that we're so fond of. All right, then you start building your transformations. Sometimes, very often, you need multiple transformations to give you a multi-step reaction that arrives using the starting materials you have, arrives at your destination. All right, this is just a little background. You can take it or leave it. If I knew more about these, I could waste more time on it, but I'm not as familiar with these guys as I am as in general chemistry. Oh, apparently this guy got a Nobel Prize for developing the retrosynthetic technique. Okay. Elias Corey. Oh, this is an editorial comment at the bottom. All of these things happened. This guy was at Harvard, and all of this happened before Harvard made itself irrelevant through woke ideologies and cancel culture and embracing academic rather than embracing academic excellence, they enforced the highest. They enforced DEI and critical race theory, and that just sent their reputation down the tubes in one big flush. Okay, here's another multi-step retrosynthetic analysis. So in this example, we want to end up with 1-methoxypent2-ine, and with starting materials of 3 or fewer carbon atoms. Right. So how many carbon atoms do we have in here? 1, 2, 3, 4, 5, 6. 6. So the least we can get away with is 3 carbon on one side and the 3 carbon on the other side. But I'm not sure we're going to be able to do that, because the alkyne, to get through the alkyne from one side, you got to go 4 carbons. So since this is a demonstration, I'll proceed. So what do we do next? How can we synthesize that with 3 or fewer carbons? So where can we make connections? Well, we know how to make an ether, right? We could draw a red squiggly line through that ether, or, yeah, that's a good place to put it, just north of the oxygen atom. And then we know how to create a carbon-carbon bond with an alkyne. Did I miscount the carbons? Continuous chain of 5 carbons. 1, 2, 3, 4, 5. Oh, the continuous chain is 5 carbons, and then the functional group is an ether. Okay, so they're right. I counted all the carbons. So we're stuck with with at least one reaction that forms a carbon-carbon bond. We can form a carbon-oxygen bond to make the ether, but we're going to have to build at least one carbon-carbon. So my guess is that we're going to form a bond on the left-hand side of that triple bond with a 2 carbon, with an alkyne. Okay? So that alkyne can have 1, 2, 3. That's the way we're going to do it. We're going to work from the left, 1, 2, between the 3rd and the 4th carbon, draw a red squiggly line, and then that'll be 1, 2, 3, and then between the oxygen and the carbon north of it, draw another squiggly line. So we can get 2 reactions here to create this compound with 3 carbons or less. Let's see if that's the way we go. Next slide. Okay, yep. There's the first squiggly line on the left. How do we form that one? Well, we need an ethyl bromide or a bromoethane. And then we need our 4 carbon is going to have 3-methoxypropionine. And then we have to take that 3-methoxypropionine and build it. Okay, so we're going probably next slide. Yeah. And for this one, we're going to have a 3-carbon alkyne with a bromine on it, and then attack it with sodium methoxide. Okay, so when we flip it around and put everything in the forward direction, that last reaction we described is first. Then we're going to take then that produces a product, right? Then that product becomes the precursor with, first of all, we have to make the alkanite ion, right? First step. Second step, we have the bromoethane, and that finishes the product. So does that make any sense? Let's see. Okay, a couple of nodding heads. That's good. Um, so let's see. I can get it out of my way, but I can't move it out of your way. A synthesis can usually be designed in multiple different ways. Yes, that's true. So very often what you have to do is just set up a proposed sequence and then go back or you can do several proposed sequences, retrosynthetic procedures, and then go look for traps, for problems. And then just by trial and error, eliminate the ones that don't look so good, that either could produce side reactions, won't produce the reaction you want at all, or even reactions that are hazardous or take hours and hours and hours to complete. Things like that. Those are types of traps that you can use to eliminate your proposed mechanism. Your synthetic step, excuse me. Get my terminology mixed up. Okay. So let's see. If we went the other route, no, that's the first one is the one we did. That group 1116 is the one we just did, I think. Or 1, 2, no, it's different. Because we have an ethine. Okay, it looks like we're just mixing up the order of the synthesis. Yeah. We're going to we're going to add an ethyl group onto that alkyne first, and then we're going to do the same reaction again to form the ether, and the ether is already there. Notice that. See that no, the second step on the right hand side, that ether is already formed. So that's another possibility. If you have a dimethyl ether, right? Most labs do have dimethyl ether, and you just have to brominate it somehow. So that's another possibility. Okay, let's see. Try to synthesize this cyanide from the hydroxyl. Well, first of all, we know that the hydroxyl is not a good leaving group. So we're not going to be able to replace it with the cyanide functional group. So probably what we want to do is replace that hydroxyl with a good leaving group like bromine or iodine. And then we can add the cyanide to it. And in this case, we're not restricted to 3 carbon precursors. That would be kind of crazy because we haven't learned how to make a phenyl group yet. Okay. So that phenyl group in itself has 6 carbons. So what we're dealing with is just modifying that functional group and creating, actually extending the carbon chain 1 carbon. All right. So will a carbon-carbon bond reaction be necessary? Yes. So we want to form a carbon bond with the carbon attached to the hydroxyl with a cyanide group. That's the one we want to break. The problem is we're going backwards. So how do we get to the cyanide? We work from an alkyl bromide, right, with a SN2 reaction, and then let's see. Let me back up. Hold on a second. I lost my place. Right. Working for the last group, how do we form that bromide? Okay, we form the bromide from the hydroxyl by phosphorus tribromide. Now we know that we can form the alcohol with an aqueous solution of an acidic solution, but it takes high temperature. It's a little more hazardous and it takes longer. So that's why we want to use the phosphorus tribromide because it works at under milder conditions. Right? We got exposed to that last week. Okay, now we've got these reactions that we think will work. So we flip it around. Phosphorus tribromide creates the bromide out of the hydroxyl, out of the alcohol. And then we attach the cyanide to the terminal carbon and bromine leaves. So there we have our synthetic pathway. Okay, we talked about epoxides. The simplest epoxide is the oxyrane. And we learned that we can open that up because that three-membered ring is under enormous strain. All right, if those carbons, those two carbons on the oxyrane are sp3 hybridized. So their ideal bond angle is 109.5 degrees. But what's the bond angle in an equilateral triangle? It's 60 degrees. So 60 and 49. So it's 49 degrees strained. And that makes these three-membered rings, these oxyranes, very reactive. We can open that up, and the oxygen goes one way and makes a hydroxyl, and then we tack on that methoxy group. So 2-methoxyethanol is the result of that top reaction. But we can also open it with a different nucleophile. Cyanide ion will attack one of those carbons and create a bond, and then break the bond and leave behind a hydroxyl on the other end of the molecule. So that's another way to extend the carbon skeleton. Now, these oxyranes can be created on terminal carbons of longer chains. They can be created in the middle of an alkane, and that way you can branch. Okay, those are just some possibilities. All right, so in this particular mechanism, we have to form the alkanide ion with sodium hydride. That's first step. Then we introduce oxyrane, and oxyrane adds 2 carbons with a hydroxyl on the end. And then we have to do a cleanup or a workup step with a strong acid in aqueous solution. Otherwise, that oxygen is left hanging out there with very reactive lone pairs. And the mechanism is below, right? Proton transfer to make the alkanide, excuse me, I had a brain fart. And then we introduce the oxyrane, form that carbon bond, and then we have the workup to neutralize that oxygen, another proton transfer. Okay, now we're going to look at something called organometallics. I always knew organic chemists couldn't get away from metals. They need them every now and then. And this is one example. So what an organometallic does, remember, metals like to donate electrons. Right? They like to become, in inorganic reactions, they like to become the cation. And non-metals become the anions. So we can look at those as donating electrons to this alkyl group. And the this is a generic. And what happens is the lithium is a spectator, and we have this ethyl anion that attacks one of the carbons and forms a bond and opens the ring. And then, of course, we still have to do the acid workup. So that way we can add 2 carbons to the length of that chain. Okay. This is an alkylithium reagent. Grignard reagents are another class of organometallics. And when we write the mechanism, we simplify it by simply making the alkyl anion with its lone pair. This allows the carbons on the alkyl group, the carbons to behave as nucleophiles because they have excess electrons. They have electron pair, usually just one. All right. So the thing about these organometallics is that they don't sit on your shelf. You have to make them. And so that's one of your reaction steps, is to make the organometallic in the reaction environment. Now we can do things to stabilize it, and we're going to talk about those in a couple of slides. You can stabilize the organometallics once they're formed in solution so that they last longer and you get a more complete reaction. That's a valid objective. I don't know about this organometallics. I guess they are commercially available, but they're very short-lived. I don't think they last very long on your shelf. They have an open by date, probably. All right. Yeah. Okay. So one, the organometallics where we have lithium in them. The other one, the Grignard reagents, have magnesium plus a halogen. So here's what an alkyl lithium reagent looks like when it's being formed. You have a halogenated alkyl group, and then you hit it with lithium, and I assume this is lithium metal. And the lithium replaces the halogen. So now we have the lithium attached to the carbon. That's your alkyl lithium reagent. The X's are usually chlorine, bromine, iodine. Fluorine's never used because fluorine's not a good leaving group anyway. Chlorine is marginal. Bromine and iodine are better as leaving groups. Grignard reaction is slightly different in that we do have a metal attached to the carbon. So we take the halogenated alkane, and then we react it with magnesium metal, and the magnesium is inserted between the halogen and the carbon. Now what this does is halogens tend to donate electrons, right? So they're donating electrons to that magnesium, and the magnesium doesn't want them. So it transfers them over to the carbon. So it's sort of a neighbors transferring pets. So that's the major difference between the lithium reagents and the Grignard reagents. And I misspelled reagent, didn't I? Look at that. Grignard reagent. Okay. The halide reactivity increases from chlorine to bromine to iodine. We already know that. This particular reagent was developed in the early part of the 20th century by Victor Grignard, who was a French chemist. And he won a Nobel Prize for it also. Interesting. These are the most widely used reagents. Now, there are limitations, and we're going to talk about those in just a minute. Right? One of those is you have to be sure to use a suitable solvent. Right? Some solvents will negate the effect of the Grignard or the alkylithium reagent altogether. Usually, alkylithium is the reaction is performed in pentane or hexane. So we know that as an aprotic solvent. There's no possibility for formation of hydrogen bonding with these. Diethyl ether can be used. It's a little more hazardous, right? Right. We used to store our diethyl ether in a refrigerator. And when we opened a fresh can and took some out and then put the cap on, before we put the cap on, we flush it with nitrogen. Because oxygen, if you get oxygen in there, the ether will form explosive epoxides, especially right around the lip of the cap. So if you ever are going to a lab and you find a bottle of ether, either dimethyl or diethyl ether, and you notice around the cap there's a white crust, close the door gently and call hazmat, because that white crust is an explosive epoxide. Now, the ether itself is extremely flammable, right? So you do all this work under a hood. If you do use the ether, I mean, there may be some case where you have to use ether and you can't use pentane or hexane. But if you do, you have to use the reagent, the alkyl lithium reagent, immediately, because there is an interaction with the solvent that is not a problem during the original reaction, but over time it does present a problem in side reactions. Unfortunately, ethyl ether, and actually, we learned that if it's a symmetrical ether, you don't have to say di. So ethyl ether is the proper name. I need to correct that. Or tetrahydrofuran are essential for using the Grignard reagent. The solvent, in this case, participates in the reaction with its lone pair electrons from the ether. Right? That oxygen, remember, oxygen normally has two bonds to it and two lone pairs. That's typical for oxygen bonding. So in this ether, you have one ether molecule on one side of the Grignard and one on the other side, donating those electron pairs to stabilize the Grignard reagent. Right? If you don't do that, then the Grignard reagent will not last long enough to complete the reaction. And here's what it looks like. So we got the Grignard reagent in the middle, and we got ethyl ether on the top, ethyl ether on the bottom, donating those electron pairs to stabilize that molecule. Now, here's a statement that I don't know why I left it in, because it really doesn't make a lot of sense to me. I'll just read it. These reactions are obviously substitution reactions. Yes, they are. Right? We know that. But they cannot be classified as nucleophilic substitutions. Now, why is that? A nucleophile has extra pairs of electrons. Right? So the functional carbon atom has been reduced. That's true. Remember what reduction is. Right? The electron receiver is reduced. So we're transferring electron pair to the terminal carbon where that magnesium is attached. And that makes that carbon reduced. And whereas the electrophilic carbon would have been well, the electrophile, it now becomes a nucleophile. So that's what confuses me, because it says can't be classified as a nucleophilic substitution, and there we go, making a nucleophile. So maybe I just ought to scratch that statement out of there, because I don't know about you, but that confuses. Yeah. Anyway, Grignard reagents are excellent nucleophiles and useful for synthetic reactions. So setting that aside, this is what it looks like when we add the metal. And we can use, we typically use either lithium or magnesium, but we've since found out that other metals can also be used. Zinc is one of them. And what happens is when you put that metal in there, the metal donates electrons to the carbon and changes it from an electrophile to a nucleophile. Okay. So, and that the advantage to that is if that carbon is a nucleophile, we can have it attack some other carbon that is an electrophile and form the carbon-carbon bond. These are some typical organometallic reagents, right? Methyllithium, butyllithium, tertiary butyllithium, where the carbon is tertiary, phenolithium, right? That's covered up somehow. No, it's still there. Okay. Or we could have a methyl magnesium bromide. That works. Or a phenyl magnesium bromide would also work as a Grignard reagent. Okay. What are the limitations? They are definitely powerful bases. If there's an acidic hydrogen anywhere in that reaction mixture, Grignard reagent will go for that first. It will take that hydrogen and will not attack a carbon, an electrophilic carbon, to form the carbon-carbon bond. So what we've done is short-circuited our reaction. If we have any acidic hydrogen, so you can't use an organometallic with an acidic hydrogen anywhere. So what's the example here is that carbonyl group, right? That makes those alpha hydrogens are acidic. All right, so you can't do that reaction. You are expecting to get, the top one says you're expecting to get, no, you're expecting to get the one with the X on it. That's what you want, but you're not going to get it. What you're going to get instead is methane and a deprotonated, a deprotonated, let's see, alcohol. So my guess is if you try to do this reaction, what would be a clue that it's not doing what you want it to? You don't even have to analyze the output, right? If you know what the limitations are and you conduct this reaction under the hood, of course, what's going to tell you that you've got the wrong reaction going there? What's one of the products? Methane. You're going to get bubbles, right? That gas is going to bubble off. And I wouldn't recommend it, but you could put have a, what do they call those little sticks where you catch them on fire and then blow them out? Mine's gone blank. but you take that glowing ember, and put it in there, and you should get a big pop from the methane. Right, that would tell you that you got the wrong reaction. So if your precursor compound has acidic hydrogens, you can't conduct this reaction. All right. Here's a partial list, right? If you've got any functional groups in there, if you've got alcohols, amides, primary amines, secondary amines, carboxylic acids, terminal alkynes, right? Remember, the effective acidity of a terminal alkyne makes that hydrogen acidic. That's why we can put sodium hydride in there and strip that hydrogen off and make an alkynide anion, because that terminal hydrogen is acidic. So you can't conduct these types of reactions, the metal organometallic reagents, you can't use on any compound that has acidic hydrogens. And that's just a short list. There are others. So, let's see. We can open an epoxide ring with a Grignard reagent. Now, my question is, are those hydrogens on the 2 carbons of that oxyring, are they acidic? You'd think that they might be acidic because of that oxygen. But apparently the strain is so great that the attack does come on one of the carbons, and you form the carbon bond with that phenyl group. Now, it's only 75% efficient, so my guess is you do get some side reactions, and you end up with 25% the undesirable product. I'm just reading between the lines here. Right? So, when we write the mechanism, we remove the magnesium and the chlorine, and we make that phenyl group an anion with a lone pair of electrons, and that attacks the carbon, opens the ring, and then we have to work up with a proton transfer from an acid. And that gives us our end product. We've added 2 carbons to the phenyl group. Okay. So these are examples of retrosynthesis where we're using oxyrain. Right? We've shown all these before, and this just puts them all in one slide. We've looked at each one of these already. All right. How do we synthesize this molecule? Begin with 4 or fewer carbons. So we've got 1, 2, 3, 4, 5, 6, 7. We got 7 carbons there. We've got a hydroxyl. I wonder if we can get that hydroxyl from a ring opening. That would be 2 carbons. 1 carbon on the hydroxyl here, and 1 carbon here or 1 carbon here. Probably on this side would be better, because that would be 1, 2 carbons there. There'd be 1, 2 carbons there. Be 1, 2, 3 here. So that's fewer than 4 carbons. All right. Let's see what the possibilities are. So what we've got here is my first idea was to have that hydroxyl group on 1, 2, 3 carbon member on the left, but we could have it on a 3 carbon member on the right. So the first arrangement, we would have to, if we're going to do a ring opening, then we would need to break the bond between 1 and 2 and add a methyl anion. Okay. That would definitely give us that those 3 carbons over there with the hydroxyl. The second bonding arrangement, we could go break the bond between, well, it shows 1 and 2, but we're not actually counting them. If we make hydroxyl the third, then the other possibility is to come from the other side. And let's see, we have one, and on that 1, 2, 3, 4, 5, 6. Okay, the top one has too many carbons on it as a precursor. The bottom one has 1, 2, 3, 4, and 1, 2, 3. So the bottom one would work better with our restrictions on 4 carbons. Okay, so we have a terminal oxirane on a 1, 2, 3, 4 carbon precursor, and then we have a propyl group, a propyl anion to do the attacking. All right, so how do we get there? Well, two-step reaction. Right, we have a Grignard reagent, and since we don't have any acidic hydrogens here, we can use the Grignard. And then we have to do the workup, an acid workup, to protonate the hydroxyl. So that should get us there. Let's see. Oh, okay. Now we're going to switch gears a little bit and talk about regioselectivity. Up to this point, we have mentioned thermodynamics occasionally, but we've been focused upon kinetics. Whichever one forms faster is the dominant reaction. When we talked about competitions between SN1, SN2, E1, and E2, we focused on kinetics. But there are cases where thermodynamics is a factor to consider. Remember, thermodynamics implies some sort of equilibrium. And remember, I haven't drawn anything on the board yet. Maybe I ought to do that just for kicks. Remember when we drew our energy diagram, and this is progress of the reaction. And say we start here with our reactants here, and then we have to go through a transition state with an activation energy, and we end up with our products over here. Right? What part of that diagram are we talking about with kinetics? This part right here. The activation energy is where we talk about kinetics. Reactants versus products, beginning and end, is where we talk about thermodynamics. And this is kinetics. So there's another feature that we have to consider. If the activation energy is very low here, very low activation energy, kinetics is dominant. But if we have a substantial activation energy, then we're looking at an equilibrium situation. I take that back. Excuse me. That's not right. It's actually the reverse. So scratch what I just said. For an equilibrium to occur, we need this energy level to be close to this one. Right? So it would be maybe out here. This would give us a discussion of thermodynamics in terms of end products. And then kinetics is actually is how big this hump is. Right. So thermodynamics, we're looking at the energies of the end products, and then we would have a reversible reaction. But for kinetics, whatever the activation energy happens to be, the difference in the reactants and product energies is much greater. So we're focused on speed of reaction versus equilibrium. That's where I'm trying to go with this. Now, these two examples, where we have both not alkenes, carbonyls. We have a terminal carbonyl here, and we have a terminal carbonyl here. And we're trying to add a methyl group here. We're trying to add a propyl group here. Neither one of these react. They do not react, right? And this is typical when an aldehyde or a ketone is treated with an alkyl halide alone. We don't get a reaction. When a strong base, like sodium hydride or sodium amide, is added first, alkylation can take place at the alpha carbon. And the alpha carbon is the one attached to the carbonyl group. Actually, the alpha carbon is part of the carbonyl. And let's go to the next slide to see the rest of it. Okay, so in order to get that methyl group to attach, what we need to do is hit it with a strong base. And then we can form a bond on the, now, wait a minute, are they calling this the alpha group? Versus, yeah, okay, my mistake. The alpha group is the one next to the carbonyl. So the carbonyl is this whole group, and then the alpha group is the one right next to it. So if we treat it with a strong base, then we can add the alkyl bromides. All right, now why is that? Okay, let's go look. So what happens is that alpha carbon, which is just next door to the carbonyl carbon, has a hydrogen on it. And we do a proton transfer. We remove that hydrogen with the base, and that leaves behind a lone pair. So we have a carbon anion. And we get enolate stabilization. We get a resonance between one and the other. Now the reactive carbon is still the one we're targeting, right? With our alkyl bromide. We're still targeting that one. But it's stabilized by this enol formation. And then the second step is the SN2, and we get the addition on that alpha carbon. Okay. Now here's the deal with regioselectivity. Alpha alkylations occur when there's only one type of alpha carbon. So for our first example, that when the tertiary carbon is the only alpha carbon we have next to the carbonyl. Whereas on the cyclopentane or cyclopental, we have two alpha carbons. So the reaction could occur on either side under these circumstances. What happens, though, if one of those alpha carbons has a methyl group on it and the other one doesn't? In other words, the one on the left has two hydrogens and the one on the right only has one hydrogen. Which one is selected for? Well, you have two possibilities. You could add your alkyl group on the left-hand carbon, or you could add it on the right-hand carbon. And here are the circumstances under which one is preferred over the other. We can control the regioselectivity of this reaction by choosing the correct base. Okay, we're going to introduce a new reagent here, lithium diisopropylamide. So the thing to think, we're going to see a structure for it on the next slide. But the important part is that both this one and the bottom one, which is tertiary butoxide anion. Those are both strong bases, and they both have lots of potential steric interference. Right? So we can't blame the regioselectivity on steric interference. There's something else going on here. Let's see. The alkoxide, yeah, the alkoxide prefers substitution on the more substituted carbon. So it's going to go to the right-hand carbon. Whereas the lithium diisopropylamide is going to go for the less substituted carbon. Now we're going to try to explain why that is, because we can't blame it on steric hindrance. So if we use this lithium diisopropylamide, the electron-rich part of that molecule is the nitrogen. And the mechanism tells us that it's going to attack, it's going to deprotonate the less substituted carbon. And that produces a resonance stabilized species. And then that one can attack the, that one can attack the brominated alkyne. And then, of course, we have to do, let's see. No, it's only 2 steps. Pardon me. It's only 2 steps. All right, so that's the mechanism for the LDA. Whereas the tertiary butoxide attacks the hydrogen on the other one, and that gives you a different stabilized resonance structure. Okay, let me go back and look at that other one. Yeah, we're still incorporating shifting back and forth between double bond carbon-oxygen and carbon-carbon double bonds, and the negative is moving back and forth. Okay, so they're both resonance stabilized. And we end up with the substitution on the the tertiary carbon now. Okay, now why is that? Okay. This is an attempt to explain why that happens. Why does LDA, why do they favor carbon deprotonation? That's the key step. The deprotonation step is the key step at different alpha carbons, because that sets the gets ready for the SN2 reaction. So here's an attempt at explaining that. I said it's not a matter of steric hindrance. It's not the bulk of the bases, because they're both bulky. Right? LDA is a much, much stronger base than tertiary butoxide anion. So what happens is it deprotonates the it favors the product side heavily. And we look at the energy diagram. So if it's a stronger base, then the products are further away from in terms of energy, are further away from the reactants. And the reverse barrier is much, much greater. So this is a one-way ticket, right? That's why in that reaction up there at the top, let me see if I can get my arrow up there somewhere. Here it is. Right there is a single arrow going to the right. That means that we don't see, this is not a reversible reaction. Products are favored in this reaction because it's such a strong base. And that means that the lithium diisopropylamide, when it's hydrated like that, not hydrated, when we've transferred the proton, then it's extremely stable. And it does not want to go back. That means it's a much higher energy barrier going back. Right. What that means is we're favoring the kinetic step, right, in that term. However, the tertiary butoxide is a weaker base, and products are not heavily favored. So it goes for the more acidic hydrogen. And the more acidic hydrogen is, I lost my place. Yes. The more acidic hydrogen is attached to more carbons. Yeah. Its effective acidity is much higher. Its pKa is lower. So when it does that, since it's a weaker base, then it has a tendency to go backwards and forwards. So we get that double arrow in there. The reversible deprotonation says now we're favoring not the kinetics, but we're favoring the mechanism favors the thermodynamics. Oh, okay. Let me replace some of these things that I got rid of. All right. So if you have reversible reactions, you get excuse me. Okay, this is a precursor statement. If you have reversible reactions to product 1 or product 2, then you're talking about thermodynamics. And you could possibly get product 1 and product 2 then from the reactions would be in equilibrium. And that's where we get the resonance stabilization that we saw in the previous slide. Okay. The species that's most stable ends up being present in the greatest abundance, regardless of how fast it's produced. So the competition then gives you thermodynamic control. If you have the potential for reversible reactions, then thermodynamic control is active. Whereas if you have irreversible arrows, then you don't get an interconversion between product 1 and product 2. Right? This irreversibility signals that you're actually talking about kinetics. So the faster reaction, wins the competition. Okay, let's see. We're going to put it in. Okay, we're summarizing here. Reversible reactions tend to take place in a thermodynamic control. and irreversible reactions under kinetic control. So let me reiterate. When we talk about thermodynamic control, that is, the reactions can be reversible, and I look at it this way. You can work back and forth, not between two products, but between reactants and products. And the energy barrier between them is very low. That's why they're reversible. But if the energy barrier is very high, and the energy outcome of the product is at a much different level than the reactants, then you get kinetic control, and that means that the more stable the product is favored under kinetic control. Okay. So deprotonation of the ketone alpha carbon takes place under kinetic control when lithium diisopropylamide is used as the base, because deprotonation is irreversible. That's kinetic control. And then thermodynamic control is the alkoxide. The kinetic control implies that the products are much, much more stable. That's because it's a strong base. It produces a very stable conjugate acid. All right. How are we doing on time? 10:30. All right. Now, we're not saying that. Actually, we're going to go to that next. No, this is not it. All right. This is a cyclohexanal. And we looked at earlier was a cyclopentanal, wasn't it? So if we take the cyclohexanal, instead of having symmetrical alpha carbons, now we have a methyl group on one of the carbons and no methyl group on the other one. If we use any base, we just pick any base, a good base, which one of the hydrogens is it going to go for? It's probably going to go for the one that's least hindered. There's less steric hindrance. Now, if it goes for the less hindered one, it's going to produce that top sequence, right? We're going to deprotonate the alpha carbon on the left-hand side. And it will resonate with the enolate, where the double bond is between the left-hand carbon and the carbonyl. If, on the other hand, the base attacks the hydrogen that is more substituted, then we resonate with a double bond on the right-hand side. And what they're telling us is that the top one is under kinetic control and the bottom one's under thermodynamic control. So what that means is that the outcome for the top one is more stable than the bottom one, because it can resonate backwards and forwards. Thermodynamic control is centered on the right-hand, more substituted carbon. So they haven't told us what outcomes yet. Let's see. That's coming. Here we go. I've got other handouts from chapter 9. Yeah, you probably want to take a look at these too. Oh, I'll leave right there for you. In the deprotonation step that produces the enolate anions, and there are two different enolate anions that are produced, which one is formed faster and which one is more stable? Right, we have to look at that as our deciding factor. Right. to determine whether it's kinetic control or thermodynamic control. So when we deprotonate a ketone at the less substituted alpha carbon, that's faster and leads to the kinetic enolate. It has fewer substitutions on that carbon. Whereas if we deprotonate on the more substituted carbon, we get the more stable enolate anion. That's under thermodynamic control. So eventually we're going to get to the point where we can modify the conditions of the reaction so that we favor one over the other. Right? So I think that's what Dr. Carty was getting at with previous slides where he said product one and product two. We could possibly get two possible products out of this reaction, and one of them's under kinetic control, one of them's under thermodynamic control, and we can control the conditions that determine which one is active, which one is dominant, I should say. Well, I thought we were going to get a slide that explained it to us. Let's see. Let me go to the next slide and see if it has it. Well, let me just add this what ifs. If we've got a base that's required to deprotonate, we don't want to conduct this reaction in an acid environment. That's obvious. So that's the choice of our solvent. So we have a basic solvent. The other possibility is concentration. Does concentration have an effect? Well, by convention, the base is going to be high concentration. So what about temperature? What effect would temperature have on whether it's kinetic or thermodynamic? Well, if it's kinetic, let's go back to our energy diagrams. Go way back to our energy diagrams. Okay. If we're under kinetic control, that first energy diagram, we've got a short hop to the top, and the differences between the energy levels of the products and the reactants. But if we're under thermodynamic control, then the reverse direction is just as likely as the forward direction. So what happens if we increase the temperature? If we increase the temperature, that generally favors kinetic because you can make it over that hump easier. So I think if we increase the temperature, we're going to favor substitution at the less substituted carbon because we've made the kinetic one way, we've made the kinetic more likely. Right? We're headed toward products with a higher frequency than, and increase the temperature on the reversible reactions under thermodynamic control, it's going to go backwards just as fast as it goes forward, right? That's the condition for equilibrium, right? Forward reaction equals reverse reaction rate. So I think if we increase the temperature, then we can control the reaction for, let me scroll down quickly. We're going to control the reaction for the kinetic. So we increase the temperature, we're going to get the less substituted carbon is going to be participate in the SN2 reaction. Does that make sense? Okay. Let's see. All right. I don't see anything new in this slide, except for different reagents. Right. Once we have the precursors established, we can write the synthetic steps, depending on whether we want the initial deprotonation to take place under kinetic control or thermodynamic control. Well, that's what I've just been talking about. The problem is it doesn't tell us how to control it unless we pick a different base. Now, that's possible, right? You pick a different base, then you get a different substitution, right? Aside from that, if you got to use the same base, then I think temperature has will help us get where we want to go. All right. Let's start talking about synthetic traps, things you have to watch out for. Synthetic traps come in different flavors. And I alluded to some earlier. I'm going to leave this up here because in chapter 21, we get into some more. Regioselectivity or stereoselectivity. Stereoselectivity is going to be something like you create a planar carbocation, and then you can attack from the front or the back. Or you carry out a reaction that has a backside attack and it reverses the stereochemistry from an R to an S or an S to an R. Multiple functional groups. I mentioned that one earlier also. If you have multiple functional groups that could undergo the same reaction, or different reactions, as a matter of fact, or the loss of functional groups in an intermediate step. I think that one's coming in 21. Loss of functional group. I'm going to abbreviate. Loss of functional groups in an intermediate step. So let's take them one at a time. Say we're trying to produce this compound on the left at the very top. And we're saying, okay, we've got this epoxide, this terminal epoxide, and we're going to use a Grignard reagent on it. The less sterically hindered carbon is attacked under basic conditions. So we make sure that the conditions are basic with our Grignard reaction, and then we do the acid workup. And we're expecting to add three carbons on the end of that chain where the epoxide is. Problem is, we don't get that product. What actually happens is that the strong base, the oxygen is protonated, and then the strong base deprotonates it. And we still have the epoxide. Only now the Grignard reagent is no longer. It's not there anymore. You just get propane. That's it. Okay. This is an example of tunnel vision. In other words, you're so focused on the outcome that you want that you force a square peg in a round hole. Just focus on the specific changes that we want to occur without recognizing other possible changes that can occur. Um, let's see. So we can apply a transform that undoes the epoxide ring opening, in which case the precursors on the right would be required. But we encounter a problem when we try to run the reaction in the forward direction. The Grignard reagent is a strong base, so when it reacts with the epoxide ring, it attacks the less highly alkyl substituted and less sterically hindered carbon. And in that middle one, 1144, notice that we're not getting the product we want. We want the terminal hydroxyl, and we end up with a secondary hydroxyl. All right, so that's one possibility is a problem. We get the wrong product. Okay. If we wanted the desired product, the nucleophile would have to attack the more highly alkyl substituted carbon of the epoxide. And it doesn't do that. And this is under acidic conditions. Right. So the mechanism, okay, so right below that is the mechanism. Under acidic conditions, then we neutralize the base and we don't get the epoxide opening. Okay, that's one synthetic trap. All right, so that's just a cautionary statement. You'll also get the possibility for synthetic traps when two or more functional groups on a precursor can react in a particular synthetic step. So that's the second one we were talking about, when there are multiple functional groups. If we want to end up with hex 4-ine 1-ol, and we think that we can take this propine and react it with 3-bromo-propane 1-ol. Well, you've got two functional groups there. And if we go by what we know so far, right, we try to turn that alkyne into an alkynide anion, and then we try to introduce the 3-bromopropane 1-ol. We don't get the desired product. Right? We just tack a hydrogen onto that alkynide, because what it's going to do, it has two possibilities. The one that we want, where it attacks carbon and the bromine leaves, that's the one we want. But since it's a very, very strong base, it's going to deprotonate that hydroxyl. Okay. And the proton transfer just leaves us dead in the water. We don't get any of the desired product as a consequence. Okay. We're going to do some retrosynthetic problems. We're not going to hit it too heavy because I'm not trying to turn you into synthetic chemists. I just want you to be aware of these things. And I'm sure there are examples in the homework that'll give you a little practice, and the practice test should give you some practice. And like the author says, developing these skills requires practice, and lots of it. And that's true for any chemical skill. Lots of practice is the only way to solve problems effectively. And I'm not going to repeat all these rules because we've already discussed them at least 2 times, probably 3 or 4 times. These are examples where you can use these samples to these proposed reactions to generate your product, and use the retrosynthetic technique to do it. So let's take all right. What I notice is that compound in the upper left-hand corner, and we're going to end up with the one in the lower right-hand corner. Let's see. Okay. All right. For this example, we're going to use these 3 reactions, actually 4 reactions, because the last one has 2 steps, and go from the top left product to the lower right-hand product. This is the overall. We want to start with this precursor and end up with this product. Oh, okay. So that's one that we do work independently. So typically what you would do is you would start with the product and work your way backwards with each of these steps using the conventions. All right. So how about this one as an example? Let's see if we can name that compound. What's the longest chain with the highest priority in it? Is hydroxyl or bromide a higher priority? Hydroxyl is a higher priority, right? The halides are at the bottom of the list. Well, they're right before you get to the alkyl groups. So this would be 1, 2, 3, 4. This would be butane. And we'd start from the right-hand side to give us the lowest numbers. So it'd be butane 2-ol, but it'd be 1-bromo. Butane 2-ol would be the name of that compound. And how about the product? 1, 2, 3, 4, 5. That would be pentane 1, 2. It'd be pent 2-ene. All right. Are we going to have to form any carbon-carbon bonds? All right. If we go from 1, 2, 3, 4 to 1, 2, 3, 4, 5, yes, we are going to have to form a carbon-carbon bond. So where's it going to be? It's probably going to be on the bromine side. So what functional groups can be converted into an alkene? And how do we apply that? All right, let's see. The target backbone has 5 carbons, but the starting material has 4. So we have to form a carbon-carbon bond. If we undo the dehydration, dehydration will give us the pi bond. So we undo that one and put the hydroxyl where it's supposed to be. Now we have to break the bond with the number 1 and 2 carbons. And the best way to do that and still get our alcohol out of it is to work from an epoxide and attack it with a lithium, an alkyl lithium group. Okay. And then how do we get that epoxide? Well, the epoxide is formed from the bromine, right? The halogen is a good leaving group, and we're supposed to make the connection between the number 1 carbon and the oxygen to form that. All right, so how do we do that? All right, so when we flip everything around backwards, then we use a strong base, and that will form the epoxide. Sodium hydroxide will do that for us. So how does it do that? Remember the mechanism? The alcohol is deprotonated, right? It forms uh, the attacking group is internal. The oxygen now has 3 lone pairs when we take that hydrogen off of it. And the carbon next to the bromine is deficient, right? So it forms a bond with that one and the bromine leaves. So now we have our epoxide. We attack the epoxide with a methyl lithium, and that opens the ring and adds a carbon. And then we have to do the acid workup. Then, if we treat it with concentrated phosphoric acid, we do an, let's see, is that going to give us an E1 or E2? It has to be an E2 because we have to form, remember, hydroxide is not a good leaving group. So in order to form the alkene, we've got to convert that hydroxide into a good leaving group. That means concentrated acid of some kind. And in this case, we're using phosphoric acid. We protonate the hydroxyl. That turns it into a water leaving group, which is a good group. Now, when it leaves, we form the double bond. And it takes heat too. Okay, so there we have our synthetic, our multi-step synthesis. All right. The last thing they talk about in this chapter is green chemistry. And I did mention that a little earlier. You don't want to use, you want to minimize the use of hazardous materials. And to do that, there's been a lot of effort recently in the past couple of decades producing with green alternatives, especially for industrial productions, because as you scale up your chemical reactions, you produce a whole lot more waste and you use a whole lot more reactants. So green alternatives have been a driving force in the industry. You want to use reagents that are less toxic too for the chemists that are conducting the experiments and the synthesis. So if you use bromine is extremely toxic. You don't want to breathe it in. Even though bromine at room temperature is a liquid, it still has a vapor pressure. So it can enter your lungs, right? So a better choice would be hydrobromic acid. Will give you the same product, along with hydrogen peroxide. How about solvents, right? DMF, dimethylformamide, is extremely toxic to your liver. Okay, it goes right in through your skin, enters your liver, and does damage. Right? So what's the alternative there? Well, we're going to use a different mechanism, actually, because DMF favors SN2 and E2 reactions. So we're going to use water instead. So we have the option of using water or DMF, along with the same azide anion. So if we need the SN2 reaction, then we have to go with an aprotic solvent. All right. So our choice of solvents is important for green reasons and for health reasons. We can also encounter other types of hazards, like exploding reactants. Diazomethane is explosive. So instead of using diazomethane, we simply use an acidic environment with methanol. And we get the same outcome. This is an esterification reaction. And actually, that's the type of reaction we're going to, well, hopefully we're going to get to in the lab today. We're going to esterify salicylic acid, which makes aspirin, acetyl salicylic acid. And we also want to minimize the byproducts of the reaction. In other words, a reaction will have the desired product, and then it will have, sometimes, it will have other products that are not desirable. We consider waste, but they have to be dealt with. In this case, we have some undesirable products with this particular reaction. So if we conduct that reaction with a different reactant, actually it's a different reaction altogether, so never mind. But there are no byproducts in this particular reaction. Okay, there's a calculation that can be done to tell us, to quantify how effective our reaction is at not producing undesirable byproducts. It's called the atom economy. And you simply take the mass of all the atoms in the desired product and divide it by the mass of the atoms of all the reagents. So here's an example. We're taking that first reaction, 1158, and we're saying calculate the percent atom economy here. So we simply add up all of the reactants' atomic weights, right? We get a value of 102.14 atomic mass units, and then we add up the, actually that's the product. The desired product is in the numerator. All the atoms in the reactants go in the denominator and divide that into it times 100. And get, in this case, we get about 21% atom economy. The higher the number, the better. Okay, now we're going to talk just a minute about percent yield. I alluded to this earlier. The more steps you have, the lower your percent yield overall, because each step is going to have its own efficiency. And the total efficiency is the product of the individual step efficiencies. So what you want to do is minimize the number of steps and maximize the efficiency at each step. For a linear synthesis, the percent yield is simply going to be the product of all the step efficiencies. Individual steps, take their efficiencies and multiply them together. And to do that, you should probably use the decimal equivalent of the percent, not the actual percent, but say if it's 50% efficient, use 0.5. So here's an example where we have 6 steps and each one is 80% efficient. Let's see. Oh, excuse me, 3 synthetic steps. Consider 2 syntheses, one with 3 and the second one with 6. Oh, okay. So the first, if we have 3 steps, then 0.8 times 0.8 times 0.8 is 51%. Whereas if we have 6 steps, we only have 26% efficiency. So that's an example, minimize the number of steps. And here we have, let's see, how many steps were in that Taxol? Was 40 something steps, was it? So the outcome was probably, yeah, a lot less than 1%. Much, much, much less than 1% because of the number of steps. Another way to deal with it is called convergent synthesis. So that's kind of like a branching tree. Rather than having um, uh, step 1 to 2 to 3 to 4 to 5, 6, suppose we have 1, 2, and 3, right? Step 1, 2, and 3, and then we have, let's see, I left out 5. Yeah, 5 and 6. And then we say, okay, we're going to take it to step 3, and then step 3 is going to be added to. That's not going to work. Let me use a slide. They do a better job of it anyway. This is an idea of a convergent synthesis. So in each one of the linear syntheses on this one, we're adding 2 carbons to each step. So we end up with 16 carbons at the end with 80% efficiency each. Now we only have 21% yield overall. But if we add 2 carbons to 2, 4, 6, and make 8 carbons, and then we do the same thing for the other part of the molecule with 2, 4, 6, and 8 carbons as our outcome, then we bring those 2 8 carbons together and make our 16 carbon, our yield goes up 41%. Okay, so how do we determine 41% versus 21? Well, we know how to do 21. You just 0.8 times 0.8 times 0.8 6 times, right? 1, 2, 3, 1, 2, 3, 4, 5, 6. And then we say 0.8 times 0.8 times 0.8 for the top leg, and 0.8 times 0.8 times 0.8 for the bottom leg. And 1, 2, 3, 4. Oh, okay. So the overall efficiency, if they're the same, is just one leg, right? Because the efficiency, we've set it up that way. So each of the efficiencies is exactly the same, just for convenience. 1, 2, 3, 4. So we only have 1, 2, 3, 4 steps in a linear sequence. And that gives us a higher efficiency. That's a convergent synthesis. Let's pick it up with chapter 21. 21 has some other reactions in it, but we're going to focus in chapter 21 on synthetic traps. Many synthetic traps are created when you have functional groups in them that we want to leave alone and attack a different functional group. And one of the ways we can get around that trap is by using a selective reagent, one that is very selective for a functional group at a particular position. The other way is by adding a protecting group to the functional group we don't want to attack, and that saves it. And after the reaction, then we have to go in and unprotect that group. And both of these strategies exploit differences in reactivity among functional groups. And when we were back in the process of naming compounds, the order of the functional groups was based upon their reactivity. The most reactive one was the highest priority, and it worked their way down according to their reactivity. Okay, so this is an example of a selective reaction. If we use sodium chloride with this particular precursor, then we simply do a nucleophilic substitution. And the tosylate is the leaving group. Right? So we got a good leaving group. We just need to select what type of attack it's going to be. Right? If the chloride is the attacking group, then it's going to attack the carbon. And if we use tertiary butoxide, that's simply a strong base that's going to attack the beta carbon hydrogens. And then the leaving group is, again, the tosylate ion. So we selectively pick a reaction which will either chlorinate the compound or it will form a pi bond. That's an example of using a selective reagent. Remember, we had competitions between substitution reactions and elimination reactions. And even though the SN2s and the E2s do tend to compete with each other, and strong nucleophiles are often also strong bases, not always, but often. We can choose specific reagents so that they selectively favor one reaction over the other, and that's what we've done here. We choose a strong base, and it goes for the proton rather than a nucleophile like chloride that goes for the carbon. All right. And this one we've looked at already, where we deprotonate with LDA versus tertiary butoxide, and we get a substitution in one location favored over the other location. Okay. So here's an example that I don't think we've seen before. This may have been one of the reactions that was introduced and we didn't go over it in class in this chapter. That's what I'm thinking. But again, we've selected a Grignard reagent in the first example versus actually, that's one I haven't seen before. It's got copper and lithium there together. And we get a substitution rather than an elimination reaction. Actually, that's not an elimination. The second one is one where the organometallic is attacking that electron-rich pi bond, right? And since we didn't cover that, then you probably wouldn't recognize it. There's so many other reactions. We just don't have enough time to cover them all. All right, how would we get from one of these to the next one? Um, so Williamson synthesis could get us from the hydroxyl to the ether, and we could do a Grignard reagent to get us to the alcohol. Or, well, if we then we reversed it, we should get the one at the bottom. And is that, I guess that's acceptable. All right. I don't think I'm going to have you do that many steps in one anyway. All right. So selective reagents is one way to um, get around that particular trap of multiple reactive side groups, multiple reactive groups. And the other way is a protecting group. So we've got this example, and this is just a generalized example. If we have this molecule with a Labour group, and we can't get from A substituted B for A, then if we put a protecting group on the Labour group, then we can do the reaction, and then we have to remove the protecting group. We have to restore the original functional group. Right? Here's an example. We've got this carbonyl, but we want to attack that A end, remove the A, and substitute a B for it. Then what we can do is change that carbonyl to a simple alkyl carbon. But the problem is, how do you go back from the alkyl to the carbonyl? Right? So we don't want to, the whole point of that series is we don't want to use that one. Right? Because we could conduct the reaction, but now we can't get back to where we were. So that would be a poor choice. All right, so here's another option. If instead we turn that carbonyl into a diether, well, let's see, they call it an acetal. Acetal is where you've got two ethers attached to the same carbon. And then once you've done that, all we have to do is add water in acid environment, and the carbonyl is regenerated. Okay. Right. You'll encounter, I mean, if you go into biochemistry, you'll encounter acetals and hemiacetals. The acetal is where you have a carbon, the R group on both oxygens attached to that one carbon. The hemiacetal is where one of those R's is replaced with a hydrogen. And you get that, for instance, the cyclic form of glucose is a hemiacetal. Okay. So here's another way to protect that carbonyl. Right? Form this five-membered ring. It's a cyclic acetal, as a matter of fact. And then all you have to do is add water, and you regenerate uh, the carbonyl. Ethane 1,2-diol. Ethylene glycol. Anybody ever heard of ethylene glycol? No? You ever put antifreeze in your radiator? That's ethylene glycol. Or a spiteful neighbor ever tried to uh, feed it to your dog? It'll kill them, right? Antifreeze. It'll cause their kidneys to shut down. Or bad moonshine. No, that's methanol. Yeah. If you're distilling your mash and you take the first uh, jug out of it and try to sell that, you'll probably either cause blindness in your customer or kill them. So the first fraction that comes off is methanol. Throw that away. And moonshiners know how to tell, right? They just do that shake test, and then you can collect the ethanol from then on. Now, ethylene glycol is it's nasty, right? And it's sweet, right? That's why dogs like it. It's sweet. They have a sweet tooth. You don't have to worry about the cats. They don't like sweet. They just like red meat. You know, birds and squirrels and chipmunks and lizards. All right. Okay, so that's another possible protecting group, ethylene glycol versus um, adding, say, ethanol. We added two equivalents of ethanol, then we get the acetal. And here we get the cyclic acetal. Either one works. Okay. So if we wanted to go from 1, 2, 3, 4, 5, pentane uh, 5-ohm, pentane 5-ohm to that product, then we could say chop it off right next to the phenyl group on the right hand side. But now we have incompatible groups. If we used a Grignard reagent to go backwards, make a Grignard reagent out of it, then we would have two incompatible groups, one on either side of the molecule, and that wouldn't give us our product. So one way is to take that carbonyl group and protect it with our ethylene glycol. Then we can proceed with the Grignard reagent. And restore the carbonyl with strong acid. Okay. Let's see. We don't need to stop at that one. So chapter 21, I think I gave you this handout as incorporated in that one handout was chapters 9, 10, 11, and 21. And this is various types of protection, depending on what you want to protect. So the first step in each one of these is the protection step. And if we want to protect that alcohol group, we can use methoxymethyl ether, form that one. And then to restore it, we would just acidify it. And it looks like not always, but sometimes acidifying will deprotect at least the first two ones. And you can get huge protecting groups like that last one, TBDMS fluoride. Okay. If we have diols, 1,2-diols or 1,3-diols, we can protect them with acetone. They form a bridge. And it just depends. If it's a 1,3-diol, that is, there's a carbon in between the alcohol groups. That's a 1,3-diol. Hexane 2,4-diol is a 1,3-diol. Then you can bridge between the two using acetone. And that'll protect those groups if you want to do something else on the rest of the molecule. If you have a benzene 1,2 diol, then the nature of that ring separates those hydroxyls far enough apart so the 1,2 will work and give you a 5-membered ring, whereas the 1,3 diol forms a 6-membered ring. But 5-membered rings are fairly stable. 6-membered rings are very stable. And then you simply acidify it with excess water, and you can restore the diols. Okay. So can we do this reaction? 3-hydroxypropanol. Excuse me, 3-hydroxypropanol. Can we go from, how do we get from there and add the phenyl group on the number 1 carbon? Okay, will that work? Wanting to use a Grignard. Grignard reagents are not just strong nucleophiles, but they're also strong bases. So the tendency is going to be for that phenyl to take a proton from that hydroxyl. So we need to protect the hydroxyl. That's where we go from here. So we're going to protect the hydroxyl with the THP. Then we can conduct the reaction and in the second step, then we just add water and acid and deprotect.